Our next talk is by Yifeng Huang from University of Michigan, the title is A Generating Function for Counting Mutually Annihilating Matrices over a Finite Field. Okay, take it away.
Thanks for introduction. So let's jump to the main result. It is quite elementary to state. So let FQ be a finite field of Q elements. Mat n denotes a set of n by n square matrices, and GL for the invertible matrices. Then we count the number of matrices, the number of tuples or pairs of matrices such that A and B commute with each other and their product is 0. And this is part of it, is a count. But the most interesting part is if I put this count into this generating function, by there is a correcting coefficient 1 over GLN downstairs. And after making this generating function, the important feature is that it has such a factorization with these explicit factors multiplied by something with infinite radius of convergence in Z. And what is it? What's the main thing it says? Naively, if we just do a naive counting on this, one can show that the radius of convergence is 1. But the main results gives beyond that. It says that it has a meromorphic continuation to all of C, and it also locates all the poles. So it is essentially infinitely fine asymptotics, stronger than a naive one. Right? So what's the motivating question behind this? So question is how many tuples of matrices of square matrices that commute with each other and satisfy a bunch of polynomial equations. Okay, and you can ask this question for any n. So we ask how this number grows with n. So it's not a random question, but actually we know a lot about a question of this kind. So here we're going to look at the algebraic variety x that is cut out by the same polynomial equations. If you don't want to think of AG right now, just think of it as the set of tuples of scalars satisfy the same polynomials, while the original question asked for the set of matrix tuples satisfy the same polynomial equations. Okay. So basically what happens is the count of these matrix tuples is determined by the count of these scalar tuples. Actually, not just the count. There's something more than a count, but it's determined by the geometry of this thing, as it turns out. And moreover, we actually know the exact count, and we know the nice generating function related to it if this thing you cut out is a smooth curve or a smooth surface. So we actually know a lot because there are already lots of flexibility. You can write some hard-looking system of equations, and if you count matrices there, it looks like a very hard question. But actually, that is already known. Okay, and then I'm going to explain like how exactly you transform this x to this generating function. So what it does is this. So the count above, you put a count above in the numerator, and you always divide by GRN of FQ, no matter how many variables are there in the defining equation of x. And then you put the generating function like this. So for example, if x is y squared equals to x cubed minus x, then what you do is you replace xy by matrices, and you copy down the equation to here. And but we always need the condition that they commute with each other. And then you divide by GLN, no matter, even though it's two variables, you just divide by 1 GLN. And then you put that this generating function, and that is the construction of z hat x z, which is a temporary notation I use myself. And since x is a smooth curve, this is actually an elliptic curve minus the point of at infinity. So the generating function is known, and in fact, it's a nice infinite product. And if you're curious about more, the infinite product involves the Hasse-Weil function of this elliptic curve. Okay, so here is the geometric interpretation for the main result. If we let x equal to xy equal to 0, it is the union of x and y axis. Then z hat x according to the rule above, it will just give you AB equals B equals to 0, and that is precisely left-hand side of the main result. And the main result actually have an equivalent statement. So if I'm reorganizing the main result, it will give you this. it says that this z hat divided by that z hat of two lines, two disjoint lines, will be the same HQ I use in the notation of main result, which is an entire function. So we can read it as this quotient is an entire function. And this is equivalent for the main result. And then now we can stare it and see what we can observe. We observe that if you resolve the singularity of this xy equal to 0, you'll get two disjoint lines, right? So this may be curious. Does this phenomenon hold for other singular curves? In other words, I conjecture that if you have any singular curve with, if this planar is not sure, is like the singularity may need to satisfy some condition. But the point is that you can predict what's the analytic behavior of z hat x by knowing what the resolution of singularity of x is. So I conjecture that if x tilde is the resolution of singularity of x, then this quotient will be an entire function in Z. And remark that Z hat x actually has some very nice property in the sense that it is local in nature. So this question only depends on the type of singularity. And the main result precisely says the conjecture holds for nodal singularity. What this conjecture predicts, it is for example, it will predict that if you take the curve cusp, which is y squared equals x cubed, and if you resolve y squared equals to x cubed, you only need one affine line to resolve it. So this conjecture predicts that this z hat function is equal to this vector to power -1 times the entire function. In particular, note that if you look at the main result for where this is xy equals to xy equals 0, the power is -2. That's because this node is resolved by 2 lines, but the cusp is resolved by 1 line. So so this is what this conjecture predicts, and hopefully this could be a concrete statement that you can use to test this conjecture. And if you are interested in verifying this particular conjecture, which is a very explicit conjecture about some asymptotics of this matrix count, you can join open problem group 2, which is presented yesterday. But if you want to join against, you can still go to the, I think there's a Google Sheet for that. Okay, so let's do some pure combinatorics now. The idea of proof behind. So recall this is a form for the main result. It says this count equal to something. So the first step is we want to make a count first. And it turns out the count is not that hard. It is actually elementary. So you can fix the rank of A first. And it turns out that once you fix the rank of A, the number of B that mutually annihilate A only depends on rank of A. So you will get a summation in terms of rank A. Rank A is from 0 to n, and then you have a summation inside. That's the left-hand side. And this is what the summation turns out. So, so it's a summation that ranges over all partition lambda. And the L of lambda is the length, and the absolute value of lambda is the size. And the one important feature that it takes that appears is the size of third field square, which is the largest square that fits inside the Young diagram of lambda. And before I go to the next slide, for a very clear picture, just make a remark that this rank A will be precisely n minus the sigma 1 lambda. So that is where the sigma 1 appears. And this is what third field squares looks like. The yellow square is the first third field square, and the green square is the second one. So in this picture, we say sigma 1 lambda is 4, sigma 2 lambda is 2. Of course, this whole thing is lambda. Okay? And the length is the vertical length. And after that, it turns out that so previously it was, so all you need to remember is that it was a sum of over all partitions. And we can rewrite the sum by, instead of summing over all partition, we fix sigma 1 and sigma 2 first. So we fix the yellow square and the green square. And the rest of the partition can be determined by filling the blank. So you fill something here, and you fill something here, and you fill something downstairs. And so that will give you a double sum in terms of sigma 1 and sigma 2. And it turns out that by symmetric cancellation, it will give you the factorization. And the final form of HQ will be something like this. So essential factor is of the form Tn squared times d to the power n. And T is, remember, T is 1 over Q, which is less than 1. So this converges for all Z. Some final remark. So the coefficient of Zx hat is actually the point count of the stack of finite length coherent shifts over X. So it has some moduli problem background in algebraic geometry. However, I don't know a geometric proof of the main result using a knowledge of this moduli stacks or anything algebraic geometry. And also the form of HQ, I haven't written down the exact explicit form, but this bounded factor is something quite complicated if you expand it out. It's too complicated that this is not likely to be a general consequence of some arguments in AG. So this means that I will be very interested to see a proof of the main result not using the explicit combinatorics, not using explicit count. So in other words, I was wondering if there is a proof that says that this equals to this times something holomorphic without even knowing what this holomorphic factor is. Okay, and then if that is done, then probably the conjecture has a hope. And finally is some very recent update. So I realized that the Z hat X of Z, I said that it is well known for X being a smooth curve and smooth surface. I didn't say what it is when it's 0 dimension. And we thought that 0 dimension will be a trivial case, not interesting. But it turns out that even when X is 0 dimension, just a point itself, the generating function is already interesting enough. And also there are several other computable cases where X is some like fat points, which means 0 dimension, but not necessarily reduced. So those include examples like this, a squared equals 0, which is x squared equals 0, or example like this. And the behavior of this seem to be entire and seem to be related to a partial theta function, which one of the typical example of partial theta function is precisely this, without the bounded factor. So just the sum of Tn squared Zn. And that has some interesting behavior in the distribution of zeros. Okay, so I'm going to end early and leave more time for question.
Okay, let's thank Yifeng for a great talk. Are there any questions? So I have a question. One, what does this HQ being an entire function tell you? Is there an intuitive sense of what that implies?
So it's more or less an observation. So
okay.
So the intuition I can only give is that you can probably say something like this is approximately equal to, so the numerator here is approximately equal to the denominator because they only differ by resolution of singularity. And this is measured by their quotient is entire function, so no extra poles.
I see, okay. And then do you know if there's any relation between this and let's say multiplier ideals or the Bernstein-Sajo functions and things like that?
Oh, actually, I don't know these fields, so I will be very interested if you can tell me more later about what they are.
Yeah, I mean, the general idea is it doesn't, it's not defined at all in the same way, but the general idea is how do you compare different singularities and they arrive at these like multiplier ideals, and somehow they seem to.
Oh, I see. Yeah, I was thinking about whether some certain invariant or quantity attached to singularity will help, but I wouldn't have any clue unless I calculate more example. But of course, this example is given, maybe experts can see something attached to the nodal singularity.
Okay, I see. Do you know in this case what this entire function is?
Oh yes, so there is actually in this case there is an explicit formula which okay, so it's basically the bounded part.
I see. Okay.
It will, yeah, it is. I can write it out later, but yeah,
Sure,
but
sure.
but it takes some time, right?
Okay. And then I guess since there's time, I was gonna ask. Admittedly, I'm not familiar with stacks at all, but what is a finite length coherent sheaf?
Okay. Oh,
I guess I always think mostly in terms of modules and their sheafification. So, and I know that a finite length module sheafifies to 0, but I don't know what a finite length coherent sheaf is.
I see. So in this case, we can actually think about when x is affine. When x is affine, then so in a quasi-coherent sheaf versus module correspondence, there's a like the tilde construction. So basically, as
Sure.
a module for a ring is nothing but a sheaf, or I should say the other way. So in this case, they correspond to module, and that those modules are so this finite length coherent sheaf are precisely like say x is spec R, the R is a ring here,
Sure.
then this sheaf corresponds to modules over R that is a finite dimensional vector space over FQ.
Finite dimensional.
And this
Okay.
will be the same category. So
I see.
you have the same category here, and then when we talk about a stack key point count, we sum over all the isomorphism class, but we also weight them by 1 over the size of automorphism group.
I see. Okay, thank you. Any other questions for Yifeng? If not, let's thank him one more time.